Thank you. So we're going to talk about virtualizing data center networks. And I know it's going to sound very trite because all of you probably have worked on something like that in your career. It started about 10 years ago or even longer time ago. We started with software solutions and then it got accelerated a bit with smart NICs. We're going to talk about, however, today, virtualizing GPU networks, which is, a different thing and it comes with its own unique challenges. So GPU network is by GPU network, I'm talking about this dedicated, separate, high performance network connecting between GPUs. It's dedicated network, often called the backend network, but it's also shared by customers, especially if you're, cloud service providers. And so we need to, come up with a good isolation mechanism, and then typically switching solutions like, VXLAN or VLANs have been used. Then we realized that now we're facing or about to face these challenges in terms of scale, feature set, and security, and even more. So we're actually observing some trend changes here from user demand side. Uh, Unfortunately, virtualizing or fully virtualizing this network comes with a lot of challenges. The biggest one, we all know that GPU network, especially accelerator networks, are extremely sensitive to throughput and latency. So how can we do this well enough in terms of performance? And second, availability. This is Burke synchronized workload. So if one of the GPU NICs goes down for whatever reasons, the whole workload, especially large workload, will end up losing tens of minutes or even more, and it's an unbearable event. So we need to ensure extreme high availability capability here. So we have to, because of performance reason, we have to accelerate this one, and then doing this acceleration without introducing high availability is one of the key things that we had to achieve. And then we're going to talk about the details today here. So before we go into more details, let me give a high-level overview of our Google, GCP product called A4. This is our latest GPU product built out of B200 GPUs. So we have pods multiple racks of GPU systems here, and then it's connected to the front-end network, the purple portion here. And then it's also connected to the green portion, the GPU dedicated fabric, high performance networking fabric. It's well optimized network architecture. And then, of course, we need to introduce this virtualization stack below the switches at the NIC layer to ensure end-host based virtualization. And then, if you look at individual nodes, each A4 VM, you can think of this as a CPU of the system, has connectivity to the GPU on the right side bottom, and then GPU NIC, and then it also has front-end NIC, our Google homegrown smart NIC called Titanium is our choice. And then of course we already have network virtualization stack there working to connect every machine to the rest of the data centers and eventually to the internet. And then what we're going to talk about today is the virtualization story that starts here at the CX7 NIC. Okay.
Okay, next I will talk about how we exactly virtualize each of the GPU NIC in our network. And after that, I will also talk about how we make this network and the GPU NIC easy to operate and troubleshoot, both for our customers and for Google as the operator. Let's start with some context for virtualization. So as Chang mentioned, this GPU network is a dedicated network, east-west network, handling primarily traffic between the GPUs. And therefore, only a suitable subset of the traditional virtualization features apply to this network. And the main purpose is to provide isolation between multiple tenants. And the main mechanism that we use to provide this isolation is through encapsulation. And at Google, we choose the PSP security protocol, which is open technology, to do this encapsulation and encryption, which assures confidentiality and integrity for all the data that travels through this GPU network. And we also need some other features from this virtualization stack to operate this network. For example, we want rich telemetry so that we can monitor the network at every layer, and we want the ability to do tracing for troubleshooting. We also want the ability to do in-service software upgrades. This is when we roll out new versions of service software, without disrupting the user workloads. And some of the cloud networking features, like VPC firewall, is also coming to this GPU network as the use cases emerge. Now let's zoom in on one of the CX7 we have in our data center. We run these NICs in the SRIOV mode, so they come up with a physical function and a virtual function. We pass the virtual function to our guest VM. So this is where our customer will run their RDMA stack and probably NIC on top of that to do machine learning jobs. In the CX7 hardware, there's a programmable block called ASAP2, short for Accelerated Switching and Packet Processing. And we program this hardware block through the Dockerflow SDK over the physical function from the hypervisor. On top of that, we run our own software, which we call ASAPD. You can think of it as the layer that translates the signals from the Google control plane into this programming in the hardware. So what does this programming look like in the hardware? With Dockerflow SDK, what we got is basically a collection of C libraries that allows us to program match action tables into the hardware. And in the tables or pipes in the Docker language, you can match on packet metadata, you can match on packet headers, and you can do modification to the packets and forward it. So this is a very flexible and powerful programming model. This allows us to create complex processing graphs, hardware accelerated processing graphs in the hardware by forwarding packets between the VM, the wire, and different tables. So here's an overview of how Google does encapsulation with this programming model. What we do is we connect all the VM egress packets or packets that are trying to leave the VF inside the guest to a root pipe. And we also connect all the packets that are arriving at the PF trying to reach the VM to the same root pipe. And in the root pipe, we match for packet metadata, we match for packet headers, we decide what the packet is trying to do, where is it trying to go to, and then we forward it accordingly. For example, for VM egress traffic, we forward it to a special pipe which does PSP encapsulation and encryption before we put it on the wire. And for incoming packets, we forward it to the decryption pipeline. And after decryption, we do decapsulation of the PSP header, we do echo check, and we decide whether we need to forward this packet to the VM or do we drop this packet if it's illegal. Now, the key question is, how much overhead in terms of performance does this bring with all the encapsulation and encryption? I'll hand over to Chang to share some interesting number.
Thank you, Weilong. So Weilong explained how we build virtualization stack, and then I'm going to show you how well it works. Okay. So the performance penalty comes in two factors: one, throughput, and second, latency. The throughput loss is basically, the number of bytes that we add to enable this encapsulation and encryption, decryption capabilities. So that's about 2% of the total, packet size, especially, if you're using large frames. People usually do not worry about that at all. Latency side. So let's look at this chart. You're looking at two bar charts here. Light blue is without encapsulation and encryption, and then dark blue is the overhead, latency overhead, or the total latency with our encapsulation stack, along with encryption here. And then you see P50 latency versus P100 extreme tail latency. And then one thing you can notice is that the gap between the two is very, very small, even at the tail end. So that's the beauty of hardware acceleration, well-tuned hardware acceleration. So we've been using this stack for our A3 Ultra H200 systems as well as B200 systems, and then we're serving hundreds of bytes of data through this stack, and we're serving again hundreds of millions of PSP connections here. We also measure the performance overhead with the real training workload benchmarks as well as nickel test. And then surprisingly at nickel test level, for example, we confirmed that our performance is actually slightly better than NVIDIA reference performance, mainly because this overhead, latency overhead, is negligible. And second, we made some further enhancement to our transport. Okay, back to Weilong.
Okay, thanks, Chang. Next, I'll talk about how we make this network easy to operate and troubleshoot. I'll share two case studies. The first is called VPC traceroute. This is our go-to stop for troubleshooting. And then I'll talk about how we roll out new software without disrupting our user workloads. This is called hitless updates. Let's start with VPC traceroute. Sometimes we get these escalations from our tenant. Hey, your network is broken. And as we all know, there are a million reasons why the network may appear to be broken. Sometimes it's just not the network. As the network operator, our first job is to tell whether this is a real problem with the network or not. And on one hand, we can easily do hypervisor traceroutes, or we can send probes between the hypervisors from one host to another host. The problem there is that this doesn't really cover the virtual private cloud data path. So for example, if you have a misconfigured firewall rules in the virtual networking, this probing doesn't discover that. On the other hand, we can also do in the VM traceroute or probing. The problem there is Google doesn't have access to our customer's VM, and it would be very unscalable if we have to ask our customer to run this command and share with us the result on every occasion. So the solution that we came up with is called VPC traceroute. This is basically the capability that we built into the hypervisor, into the hardware, that allows our hypervisor to craft and inject probe packets into the exact same data path as if these packets come from the VM. And then on the ingress side, we also match and intercept these packets, and we drop them before we deliver to the VM, because otherwise the customer would be very confused, like, what is this packet? And to achieve this, to identify what packets are these crafted probe packets, we utilize the sample and drop bits in the PSP header. And if and only if both bits are set, we treat this packet as a probe packet generated from our hypervisor. And in terms of the pipeline in the hardware, we also connect this into the same root pipe that you saw previously for PSP encapsulation. When we craft such packets, we craft it with a metadata set to some magic value. And in the hardware, we match for this magic value. And if we do see it, we know that this is a probe packet. And then we forward it normally to the PSP encapsulation. And after that, we forward it to a special pipe where we set this sample and drop bits in the PSP header before we put it on the wire. And at ingress, we will match on the S and D bits in the PSP header before we do decapsulation, and set some packet metadata to remember later. And then before we deliver the packets to the VF, we match and intercept such packets. So here's a screenshot of the VPC traceroute in action. This integrates seamlessly with our existing CLI and Web UI tools. So with a single line of command, we can basically probe any pair of the GPU in our massive GPU network and be able to tell whether there's a black hole in the network between the pairs or not. And next, I will talk about how we do hitless updates. So as you can imagine, we need to roll out new versions of system software, ASAPD in this case, to the cluster to either roll out new features or roll out bug fixes occasionally. And the naive way to do this is we can shut down the old process and just kick off the new process. The problem there is if you shut down the old software, the process closes, and the file descriptor that is associated closes, and the NIC actually cleans up the resources. So you lose all the forwarding state, and your GPU suddenly stops have connectivity to the outside world until the new software kicks in and starts to program these forward state in the hardware. And the new software takes time to initialize. For 8 CX7s, it takes about 20 seconds in our experience. So this means you have 20 seconds of lost connectivity for GPUs. This translates to your RDMA QP timeout. This translates to a training job now has to abort. You have to restart from a checkpoint. And the worst case is if you have a large-scale cluster, you have thousands of nodes, and if we do a rolling upgrades, and each of the nodes goes down for 20 seconds, this renders the entire cluster unusable for tens of minutes or even hours, which is clearly unacceptable. So the way we do hitless update from the high level is that before the upgrade, our software is running, this blue ASAPD is running. It programmed the NIC with some forwarding state, some PSP tunnels, and then packets are flowing happily between the VF, the wire. And once we decide to roll out a new software, we'll kick off this new process, the green ASAPD, new version. In parallel, on the side, this new version actually programs a standby flow database in the hardware. No packets touch this hardware at this point. All the packets still go through the old database managed by the old software. And the new software can take its time to initialize. And once it initializes, we start this handoff process. The old process hands off the business state or the PSP tunnel to the new software. And the new software starts to program the forwarding state into the standby flow database in the hardware. And once it's done, we kick off the switch. And the hardware, now all the packets flow through the new flow database served by the new software. And it is safe for us to now decommission the old software and tear down the old flow database. So next, I'll hand back to Chang to share how this impact our rollout in real world.
Well, how it doesn't impact our rollout. That's what we wanted to show here, right? Okay, so in this chart, I'm showing you a time series of our ASAPD releases, including both control plane and data plane updates. And then each color here means a different release version of our stack, network virtualization stack. So you're looking at about 2 weeks of time period of our history last year, October, late October. And then at any point in time, you have 2 or even more ongoing versions out there. And then the migration is quite seamless. And as you can see on the y-axis, the total number of virtualized network endpoints keeps increasing. Okay, so to summarize, we have briefly showcased how we did GPU network virtualization using the stack that we have customized, built on top of a tool that is actually publicly available. So one of the reasons why we came out and then shared this is because the tool is at least public. So if the industry can actually use these tools together, it would be a great opportunity for us to harden and improve this stack together. Okay. And then we also showed you how we can ensure high performance and also high availability, more importantly, using this stack. So thank you very much.